All right, folks, that one's going to be a very quick one. And in all actuality, I could have combined this short lecture of this video to the previous one because it turned out that the previous one was not overtime. I had the impression that I had been deriving equations forever and that I was, I had been camcording myself like for 2 hours or something. Turned out it was about only an hour. But the previous one combined with this one is actually going to be an hour and 20 minutes maybe. So again, a quick one just to finish off this chapter 4, and then we'll be on our way to the last chapter of the semester, which is going to be chapter 5, and specifically looking at how can we apply the theory you saw in feedback control system and apply that great theory specifically to the problem of spacecraft attitude control in terms of active control using onboard actuators this time. Okay. Now that we had obtained the equations of motion in terms of roll, pitch, yaw dynamics in 4.4.1, next step is to look at the stability. And because the pitch equation of motion is decoupled from the roll and the yaw equations, we're going to first look at the stability of the pitch motion. Okay? So the first step to do that is just to re-express what we had for the pitch equation by dividing everything with jy, such that we end up with a ratio of inertias, like that, multiplying 3n squared, which is a constant, times the dynamical variable of interest, okay? So we have the acceleration of the angle plus a constant times the angle itself equal to 0. This is then easily understood as a linear differential equation of motion. And we have all the tools we need to analyze that. I'm going to say theta double dot plus, I'm going to replace all this term here with n. Oh no, not n. That'd be silly, right? And it's already used for the orbital motion. I'm going to replace it with alpha. Yeah, alpha theta equal to 0. So same old, I'm going to use the Laplace transform on that equation, not forgetting about the initial conditions. So this term is going to turn into s squared of the theta angle in the s domain minus s initial pitch angle minus initial rate of change of that angle here. Let me express everything. Well, those are constants, so it doesn't matter. Minus. Plus alpha and angle in the S domain, like this. So what I can do next is solve for theta S in the S domain. Okay, so if you have S squared plus alpha, these two multiplying theta S, and then equal on the other side to S theta naught plus theta naught dot, like that. Or alternatively say that theta S is going to be equal to the initial conditions over S squared plus alpha. Yes, yes, we like that kind of transfer functions, don't we? Because it is so simple from there to analyze the stability. Because all we have to do again is look at the denominator and say that we're going to set this denominator equal to 0, or in other words, we're going to write what's known as the characteristic equation for this variable equal to S squared plus alpha equal to 0. Okay? And from there, extract the poles by solving this characteristic equation for the S variable, which is going to be equal to square root plus minus square root of minus alpha. Ah, haven't we seen that in the past? Yes, we did. Okay, we did in the spin stabilization technique. So just based then on the value for alpha, we're going to get different pole locations in the complex plane or different behavior. Maybe we're going to get unstable behavior or stable behavior, or if we're lucky, asymptotically stable behavior, which is not going to happen. As a heads up, that'd be cool. But to get asymptotically stable system, we do need to apply torques actively using onboard propulsive components like thrusters, or using reaction wheels. Those are wheels that can be accelerated and decelerated, okay, accordingly. But in terms of passive stabilization, the best we will be able to achieve is stability. So case one is whenever alpha is larger than 0, such that the pole locations end up at plus minus j square root of alpha. This is a pair of complex conjugates in the complex plane, real axis, imaginary axis, boom, boom. This one is at j square root of alpha, that one at minus j square root of alpha. And as you know by now, this is a stable behavior in terms of Lyapunov stability, because that would generate bounded oscillations in the time domain. So this is good. Makes you happy, because if alpha is larger than 0, then you get a pitch motion that is stable. So the spacecraft is originally perfectly aligned in terms of its body fixed frame to the roll pitch hour reference frame. Okay, Bx is aligned with Qx, By along with Qy, and Qz along with Bz, such that the spacecraft has its z unit vector pointing straight down in the nadir configuration. While if the pitch starts to deviate a little bit, or if there's a slight deviation between body fixed and roll pitch hour reference frame, then it means that this deviation in pitch will not grow larger with time. It will just swing back and forth along the pitch axis, or about the By direction, okay? It will never go back to 0. The pitch will just keep oscillating. Okay, if this is pitch angle, you would see that kind of motion. But it's not ideal, but it's way better than having something which would grow with time, okay? So stable behavior is always good for passive stabilization techniques. Case 2 is obtained whenever alpha is equal to 0, which means that this translates into 2 poles at the origin of the complex plane, which means that this is an unstable situation. Makes you sad. Unstable in the sense that the growth and amplitude of the pitch angle would be linearly increasing with time. Not too fun. It'll be quite a roller coaster, okay? Case number 3. If you have alpha less than 0, you end up with poles that are located at less than 0? Yeah. Plus minus square root of alpha, meaning that you have a positive pole here and a negative pole here. That's your negative square root of alpha, and that is a positive square root of alpha right there. And this is the worst of all situations. And that makes you sad as well, right? Because that would be an exponentially diverging oscillations. Whoa! Like that. So all in all, if you want to get a stable pitch behavior, thanks to gravity gradient, you better satisfy this inequality here. That says that alpha has to be larger than 0. And if you go back to the definition of alpha that we had set, that implies that this condition turns into satisfying Jx larger than Jz. Doing so means that you're going to generate stable pitch motion about by unit vector or about qy unit vector. Okay, so the angle in terms of deviation would remain stable with time. That's the only way. Okay, but what about the Rowley motion? The two equations of motion that were coupled together. Well, let's have a look at that. Four point 4.3 x and y coupled equations of motion in terms of stability analysis. Okay. What you have to do to begin the process is to go back to the x and y equations we had obtained during our last lecture. These set of last three equations we had on the board here. Pick the first and the third one and just divide everything with jx and jz respectively to obtain the roll acceleration equal to, or minus rather, jx minus jy plus jz, all this over jx, and this multiplying n times the yaw rate plus your 4n squared term that we had times jy minus jz over jx times roll angle equal to 0. That was the equation for x divided by jx. And you take your z equation and you divide with jz all over the place to obtain the yaw acceleration plus this ratio of inertia jy minus jx over jz times yaw angle. Okay? And then what I'm going to do is to rearrange those two terms here to my advantage. Specifically, I'm going to say that jx over jx is 1 here, and that my jz over jz is 1, such that I can write the whole thing as being equal to, and I'm going to turn that into a plus sign, to then write plus jy minus jz over jx minus 1. Okay? So I'm flipping the sign, and I'm separating the fractions such that I have my jx over jx term on its own, and then replace this with simply 1. Okay, this is equivalent to before. And here I'm going to do a similar thing. So I'm going to say jz over jz is 1, and minus jy minus jz, or minus jx over jz. Okay. Such that this is 1 minus jy minus jx over jz. Okay, just like that. And the reason why I wanted to write things this way is because I have repeating terms now. Right now, this is equivalent to that. And we've got this one equivalent to this one, such that I'm going to replace these, which are simply constants, right? Ratios of inertia are constant numbers. I'm going to replace that with a new variable denoted K1 and K1 over here as well. 1 phi equals 0. And I'm going to call this guy K3 for no good reason, just another variable, and replace this with K3 as well. Because I don't want to carry those fractions in the follow-up development. That would just be too cumbersome. Like this. So let me see here. This is n5, n squared K3 phi. Yes, yes. Where obviously my K1 had been defined equal to whatever it was replaced with. So that's this over Jx. And my K3 was set to be equal to whatever I had in terms of ratio of principal moments of inertia, like that. Okay? Now, what I'm going to do is that I'm going to skip a few steps and do the work for you. Okay? So I'm going to write that into matrix form. Then take the Laplace transform. And then look at the denominator of what I would get and end up with the same denominator in terms of expressions for both relationships. Okay, exactly as we did in the past when we analyzed what's the pitch, not the pitch, but the spin stabilized motion, I believe, or was that in the torque-radical motion? Anyway, we had written things in terms of matrices and then re-express those expressions to figure out what would be the denominator of those two expressions. And because they are equal to each other, it means that the dynamics of the roll and the yaw motion here will be exactly the same. And that's the situation we end up with. Okay, so skipping a few steps ahead, I've applied the Laplace transform. I've expressed everything in a matrix form. I've been able to extract the denominator of those two equations, and then I can use the denominator to get my characteristic equation, CE, which is simply the denominator set to be equal to 0. For K1, K3, and to the power 4 equal to 0. Now the problem here is that we have an equation to the power 4, so solving for the roots of that equation or solving for the poles of that system is not that trivial to do by hand. But what you have to realize is that we have a variable to the power 4, constant, times a variable to the square, and then just plus some other constant at the end of the day. So what you could do essentially is solve that for the s variable or solving for the roots and figure that they would become complex conjugates if and only if K1, K3 is larger than 0, if 1 plus 3 K1 plus K1 times K3 larger than 0, and also if this last inequality is satisfied as well. Square minus 16 K1 K3 larger than 0. And now you probably understand why I didn't want you to do that by hand, and I didn't want to do it by hand for you on the board, okay? Because these are the conditions that would ensure that the poles of this characteristic equation and the roots of that characteristic equations end up somewhere stable, okay? Because this is the best we can do again. There's no way that we can get those poles to be on the left-hand side only of the complex plane. The best we can do is to get them on the imaginary axis without having anything on the right-hand side of the complex plane, or having a duplication of poles, say at the origin or along the imaginary axis. Okay, so these are the necessary conditions that we need to satisfy to ensure roll yaw stability, and we have to relate those three conditions to our definition of K1, K3. And again, we're not going to do that here on the board because that would be quite a bit complex to do by hand. So again, instead, I'm going to relate that for you to what it means in terms of the principal moments of inertia by virtue of our definition of K1 and K3 we had used to simplify our equations, okay? So ultimately, this means that Jy minus Jz has to be larger than 0, and that Jy minus then Jx has to be larger than 0. Or equivalently, that means that Jy has to be larger than Jz and also larger than Jx. Furthermore, we had obtained from the pitch motion stability the fact that Jx has to be larger than Jz. Or, altogether, that Jy needs to be your major axis, the largest entry in the inertia matrix, that Jx needs to be the intermediate axis of rotation, or the intermediate value in the inertia matrix, and finally that Jz has to be your minor axis of inertia or minor axis of rotation. So that makes a lot of sense because I had begun this section by saying that gravity gradient would want to naturally align the minor axis of rotation of the body fixed reference frame towards the Earth. And guess what? The minor axis happens to be dz. If the spacecraft is designed by careful placement of components within the rigid body or mass distribution, end up with an inertia matrix that satisfies those three things, then naturally the spacecraft will want to align itself with the roll pitch yaw reference frame at all time and maintain the nadir orientation throughout an orbit, okay? But it's BZ unit vector pointing down like that. And the reason why we want BZ specifically pointing down is because QZ is also pointing down. Okay, so we want to have those two vectors aligned, and we want BX aligned with QX and BY aligned with QY. And that's why we have this kind of stringent requirements here. We don't want to have any axis oriented downwards. We do want to have the minor axis pointing down. We do need to have the intermediate axis pointing along being BX and pointing along QX. And finally, we want to have the major axis to be our BY or pointing towards QY. okay? Doing so, should the spacecraft ever deviate slightly from the ideal orientation, well, gravity gradient will put it right back in, right back down, okay? Now, there's a couple of things you can do to enhance this effect, such that gravity gradient has a larger torque in terms of restoring torque on the spacecraft itself. And that comes down to the expression we had obtained on the right-hand side of my three equations, where I had the gravity gradient torque and the body fixed reference frame. And I had then told you that we're going to use an alternate expression for gravity gradient torque and body fix. That could be derived from the first expression, but that was up to you to do that derivation because it was one of the problems in this chapter. Now, if you go back to this alternate expression, you will realize that the torque is actually proportional to the difference in principal moments of inertia. So to maximize the efficiency with which the gravity gradient torque restores the spacecraft orientation always in the nadir configuration, well, the trick is simply to maximize the difference of your principal moments of inertia, okay? Because gravity gradient is proportional to the difference in principal moments of inertia. And one way people do that in practice is by putting on their spacecraft large gravitational or large deployable booms, okay? Think of that as rigid rods that get deployed in orbit. At the end of both are big masses, such that all of a sudden the inertia matrix of the spacecraft is greatly changed compared to the case where those two booms were stowed inside the spacecraft. So you are maximizing the difference in principal moments of inertia by deploying two booms along a single axis, and thereby, by doing so, you maximize the gravity gradient capability to passively stabilize the spacecraft, okay? Those two booms are referred to gravity gradient booms for that specific reason, okay? And you can look up the web for gravity gradient stabilization spacecraft, and you will notice that a lot of them have those gravity gradient booms being deployed, because again, that maximizes the hold, if you will, that gravity gradient has in that spacecraft to torque it and restore its nadir pointing orientation. So for small CubeSat applications where we want to say to always have the camera facing down at the Earth throughout multiple orbits, this is a cheap and easy way to maintain the orientation of the spacecraft in that configuration. Now, that would get perturbed on orbit because, you know, drag is there, solar radiation pressure is there, magnetic torque is there. So all those effects have a torquing effect on the spacecraft. Not only gravity gradient is acting on the spacecraft, which means that we're going to get roll pitch angles equal to non-zero values at all time, right? It's going to swing back and forth, but still that swinging motion will remain stable. Or in other words, roll pitch angles that define the orientation of the spacecraft with that nadir direction, or with roll pitch reference frame, same thing, will be bounded and will oscillate, but will not grow unstable. And here we're talking about a pointing accuracy in a nadir direction of about maybe 10, 12 degrees. So it is not super accurate. Still, it would maintain a rough orientation of your spacecraft, always pointing down at the ground. Okay? If you require for your particular application a much tighter pointing accuracy, say you want a spacecraft to be always within 0.5 degrees of a desired direction, then forget about passive attitude stabilization techniques. Those techniques are free, easy to implement, but the accuracy you get out of those are kind of coarse. So if you want to find pointing accuracy, you need to turn to active feedback control system techniques and employ actuators on board, small thrusters, reaction wheels, control moment gyroscopes that will torque the spacecraft in real time in an active way to always make small corrections, to always fight any perturbations that are trying to push the spacecraft around. And that, ladies and gentlemen, will be the bulk of Chapter 5, okay? So how to design active feedback control systems to improve the accuracy with which we can maintain or point our spacecraft in a given direction. All right? I'll see you again in the next lecture where we dive in Chapter 5. Till then, again, keep up the good work, and I'll see you soon. Goodbye, guys.